Let's look at the construction of the physical model of the heat equation. So the idea is that we want to track the temperature distribution on a domain. So we have a domain omega, that is the area in physical space we're interested in, and we want to associate to every point in omega a temperature. And this temperature can change over time. So we are constructing a function, capital T, that goes from position and time to a value that we're going to call temperature. And we want to look at how T value varies over omega and over time. And we're going to look at how does heat distribute. The key element to understand how heat distributes, it's going to be this Q, is called the heat flux. Is the amount of heat crossing a unit area over a unit time. It's a primary concept akin to energy flow. What you want to think about is that if there is heat here and no heat there, then heat is going to be traveling through a unit area, and you can track it by looking at the heat flux. As my example can point at, the heat flux depends on the temperature gradient. So the temperature gradient means how much temperature is changing depending on where you are. If there is the same temperature all over the place, then there is no flux because everything is stationarily distributed everywhere. While if there is more heat in one place and less heat on the other, you're expecting more heat to move towards less heat and average it out. That means that the heat flux, Q, flows from high temperature to low temperature. So it must be, at its simplest level, equals to minus a positive coefficient times the temperature gradient. This positive coefficient that I indicated by alpha squared, so it's obvious that it's positive, is the conductivity of the material. It kind of indicates how easily the temperature can move. This law here, we call it the Fourier law, and it depends on the material, is a constitutive law. That means you looked at the material and you determined that that specific material satisfies this law. It's a law that is built up on experiments. There might be materials that do not satisfy the Fourier law. They might have more complicated heat distributions properties. And we match this Fourier law with the first principle of the conservation of energy. So notice how these two things are on different levels. The one is a first principle. Conservation of energy needs to be satisfied all the time in every single physics model you're going to be seeing. While Fourier law depends on the type of material you're looking at, and it's only determined for experiments. It's not a first principle. But we're matching this. We're looking at the conservation of energy, tracking the change of temperature in a fixed volume depending on the heat flow in and out of the volume. So what we say is that the change over time of the temperature times the heat capacity of the volume itself on an infinitesimally small volume is equal to the heat flow in. That means the temperature is going to change depending on how much heat you can store on the infinitesimal volume and depending on the heat that is coming in and out. We're going to be computing both at the same time. So how do we compute the heat flow? By computing the integral over the boundary of the infinitesimal volume of the heat flow, heat flux Q, times n being the outward normal of our volume that we're looking at. So we take this heat flow, the passage of the heat flow through your infinitesimal volume, and you match it with the information we had about the change in temperature on the infinitesimal volume depending on the temperature and the heat capacity. So we have this formula. And we apply the Fourier law because we know that the heat flux depends on minus alpha squared delta T, gradient of the temperature. So the minus sign cancels out. And now we can use the divergence theorem. We replace the product with the normal over the boundary of the volume with the integral on the full volume of the divergence of the element. So now we have the divergence of the gradient, and that is the Laplacian. So we replace this for the integral over the volume of alpha squared delta T, dx, dt, dz. So now we have an integral heat equation. It's an integral heat equation that is valid for every infinitesimal volume V. So we can just drop the integral altogether because it's valid everywhere and have this new equation, derivative over time of the heat capacity times the temperature minus alpha squared Laplacian of T equals to 0. Assuming that the heat capacity is constant over time, then we can take the CV out of the derivative with respect to time, and we retrieve the heat equation. We only have a first order derivative with respect to time. That means that this equation is parabolic over the four-dimensional problem x, y, z, and t. This is just a reminder of what is the Laplacian of t, is the sum of all the second order derivatives non-mixed with respect to every single variable.